Hi everybody, this is our last video in a series on optical mineralogy, and today we'll be covering biaxial materials. Last time we covered the specifics about uniaxial materials, and we'll do a brief recap now of what we learned in that video, because it will be helpful in understanding biaxial materials. We learned that our uniaxial materials are defined by two refractive indices, and that the way these are arranged results in these materials having a single optic axis. The optic axis is a single direction in which light traveling through the crystal essentially behaves as though it's traveling through an isotropic substance. For our uniaxial materials, the optic axis is always going to be associated with the C crystallographic axis. Identifying a substance as uniaxial means it must either belong to the hexagonal, trigonal, or tetragonal crystal system. Here's an example of how the optical properties and crystallographic axes align for tourmaline, a uniaxial mineral. We talked about how our optical properties can help us to determine which crystal symmetry system a mineral belongs to, and summarize that information in this handy figure. There's a further subdivision of uniaxial minerals by optical properties as well, and these two classes are uniaxial negative and uniaxial positive. In uniaxial negative materials, omega is greater than epsilon, and in uniaxial positive materials, epsilon is greater than omega. We then put our newfound knowledge to work trying to understand corundum and its optical properties. Using the optical indicatrix for corundum, we figured out how we can align the optical phenomena that we see with the crystallographic axes of our corundum. Using a synthetic sample of corundum cut in very specific directions, we were able to identify when we were looking down the plane of the A-axis of the corundum or looking down the C crystallographic axis. We then demonstrated how to generate a uniaxial optic axis figure, and this figure is diagnostic for identifying a material as uniaxial. We also talked a bit about how our corundum varied from the ideal due to some residual stress in the material. Our main take-home, however, is illustrated by this figure. Basically, if we know any two of the three concepts, we can figure out the third. So let's get started on our biaxial materials. So our biaxial materials are going to be defined by three refractive indices. Last time we talked about how you can generate optical indicatrices for isotropic and uniaxial materials. The optical indicatrices, of course, being three-dimensional representations of the refractive indices of a substance. And these are relatively simple shapes. For isotropic materials, it's going to be a sphere. For uniaxial materials, it's going to be either an oblate or prolate spheroid. For biaxial materials, however, things are going to get a bit more complicated. So the biaxial optical indicatrix is known as a triaxial ellipsoid. This shape can't be generated by imagining a two-dimensional form rotated around an axis like we did with our isotropic and uniaxial indicatrices. So instead, we're going to generate this three-dimensional figure using three two-dimensional elliptical sections. And the axes of these elliptical sections are going to be the refractive indices for our biaxial material. These three refractive indices are referred to as alpha, beta, and gamma, with alpha being the smallest, beta being an intermediary index, and gamma being the largest. So if you imagine putting together these three mutually perpendicular ellipses in order to form a three-dimensional figure, it would look something like this. So I also want to mention that these three views of our optical indicatrix, looking down on the gamma-beta plane, the alpha-beta plane, and the gamma-alpha plane, are going to be three very important views for identifying biaxial materials. Well, now that we have our optical indicatrix, we should be able to figure out where the optic axes should lie for this. If you remember back, you'll recall that I've said biaxial materials are going to have two optic axes. And you'll recall that for our uniaxial materials, the optic axis was perpendicular to our circular section. So now we just need to figure out where our circular sections are going to be in our biaxial indicatrix. And if you've managed to spot them, you're pretty awesome. It took me a really long time to figure this out. So our circular sections are actually going to be located here. Planes cutting through this portion of our optical indicatrix will result in circular sections with refractive index beta being the radius of our circle. Now that we've spotted these, we know that perpendicular to these circular sections will be our optic axes. And so here are the optic axes. These two optic axes lie in the same plane and are going to give rise to another measurement we can make to help us identify our biaxial materials. This measurement is the angle between the two optic axes and is known as our 2V angle, as shown here. So what determines the 2V angle? Well, it's going to be determined by how close beta is either to gamma or alpha. And this takes us into our next distinction, which is whether a material is biaxial negative or biaxial positive. Our current optical indicatrix is actually biaxial negative. And what that means for us is that our beta value is actually going to be closer to gamma than it is going to be to alpha. And that means our optic axes are more closely huddled around the direction of our indicatrix associated with alpha. But this doesn't have to be the case. There's a whole bunch of other triaxial ellipsoids out there. And let's quickly build an optical indicatrix for an example in which beta is closer to alpha than it is to gamma. Two-dimensional ellipses, check. Three-dimensional indicatrix, check. Slap on appropriate circular sections of length beta, check. Add in optic axes perpendicular to said circular sections. And now you'll see our 2V angle actually is going to be huddled around gamma. So here we've come up with an optical indicatrix that is biaxial positive. I should mention a couple special cases too for our biaxial indicatrix. One is if the 2V angle is 90 degrees. And what this means is that the indicatrix is neither positive nor negative. And this state occurs when beta is halfway in between gamma and alpha. The other is when our 2V angle is 0 degrees. And what this means is the material is actually uniaxial. So if you really wanted to, you could just think of uniaxial things as a special subset of biaxial materials. Sort of like how all squares are rectangles, but not all rectangles are squares. So I have one more quick concept to mention before we get into looking at actual minerals. Just a bit of nomenclature. When we build our optical indicatrix, we use our refractive indices alpha, beta, and gamma. But when specifically referring to directions, usually these are called x, y, and z. X being the direction along which alpha is the refractive index, y being the direction along which beta is the refractive index, and z being the direction along which gamma is the refractive index. Going forward, I'm just going to probably be using alpha, beta, and gamma mostly, but just so you know that the directions are actually referred to as x, y, and z. So we've made it to our fun mineral. Hooray! So what we'll be looking at today is a piece of Cordierite. This mineral is also known as iolite in the gem world, and we're using it today because it has some really strong pleochroic colors which are going to make it easy for us to identify alpha, beta, and gamma. So just to help orient us, I've cut and polished this piece of Cordierite in very specific ways, leaving one face remaining that is associated with the cleavage direction of Cordierite. This cleavage direction is perpendicular to the B crystallographic axis of Cordierite. And so if we're looking down on this cleavage face or through this cleavage face, what we're actually doing is also looking down the B crystallographic axis. And with that knowledge, let's break out our Cordierite optical indicatrix. So just note that this isn't to scale, and also that there's a whole pile of caveats we'll be talking about later. But for Cordierite, which is an orthorhombic mineral, all our crystallographic axes are going to align with important directions through our optical indicatrix, meaning that, in particular for Cordierite, the B axis is associated with gamma, the A axis is associated with beta, and the C axis is associated with alpha. Also, by looking at the relative values of alpha, beta, and gamma, you should be able to figure out that Cordierite is going to be biaxial negative. So, if we're looking down our B crystallographic axis, which view of our optical indicatrix should we see? Looking down the B axis, which is associated with gamma, means that we should be seeing the alpha-beta plane. So let's take a look at our crystal now in plain polarized light in that direction and see what we can come up with. So our view is perpendicular to our cleavage direction, and we should be looking down the B crystallographic axis onto the alpha-beta plane of our optical indicatrix. So as we rotate, you'll notice the crystal darkens, and it darkens quite significantly. You can kind of see a bit of the really deep blue color that is being transmitted. So just like with the uniaxial materials, for any particular view of this crystal, as we rotate, if we have pleochroism going on, every 90 degrees we're going to transfer from a one pleochroic end member color to the next pleochroic end member color. So just to illustrate that point, what we'll do is a full 360 degree rotation of this, and you can see we're going to go from our nice dark blue here, then back to the very light clear color. So if I cut this sample properly, we know what we're seeing. We're seeing one pleochroic end member color associated with alpha, and one pleochroic end member color associated with beta. Much like with the uniaxial minerals, however, if I ended up cutting my sample a little bit off, what we'd actually be seeing is an ellipse with alpha prime in it instead of alpha proper. So now that we've done our full 360 degree rotation, let's bring in our upper polarizer and confirm that the maximum and minimum colors that we're seeing here are associated with alpha and beta. Remember, under cross-polarized light, we shouldn't see any light transmitted if we are seeing only alpha or beta. And as we bring in our polarizer, we see that the sample is dark, so this orientation is giving us a view of one of our end member colors. And as we begin to rotate the sample, you can see light is starting to be transmitted, maximizes at about 45 degrees, and we return to darkness 90 degrees from where we started. So you may be saying to yourself now, hey, I buy that we're looking down at the alpha-beta plane, but how do you know which color is associated with alpha and which color is associated with beta? Well, thankfully, we can just look these optical properties up. For Cordierite, the pleochroic end member colors are pretty well known. Alpha is associated with a light color, and beta is associated with a deep violet color. Now there's one caveat here that we're going to run into with a whole variety of different minerals, and that's simply that many minerals exhibit solid solution series. And our Cordierite falls into this camp with a solid solution series between magnesium and iron. Basically, these two elements are similar enough in ionic size and charge that they can exchange in a particular site in our Cordierite. And what this means is that our optical properties are actually going to vary along with our solid solution series. So we can have Cordierite that's entirely magnesium, or we can have Cordierite that's a blend of magnesium and iron, or we can have Cordierite that's entirely ferroin. So while this makes life somewhat more complicated for us, it also gives us an interesting tool in order to figure out something about the chemistry of our Cordierite just based on the optical properties. And we'll see this trend in other minerals. Basically, iron is going to be a source of color because iron has d orbital electrons. That's as far down that rabbit hole as we'll go in this video. But that was all just to point out that our pleochroic color scheme for Cordierite is actually for iron-rich varieties of Cordierite. So let's get back to our Cordierite now and use our pleochroic scheme in order to figure out our crystallographic directions. So the first thing we noted about our Cordierite is that we used our crystallography and a cleavage plane in order to figure out what direction we were looking. And so with our viewing direction perpendicular to that cleavage plane, we know we're looking down the B axis of our Cordierite, which, according to our optical indicatrix, is associated with refractive index gamma. Further, using our optical indicatrix, we know that this view must be looking down on our alpha-beta plane. But we were stymied in figuring out which of our pleochroic end member colors was which. Without further information, we can't really tell right now if we're aligned with alpha or if we're actually aligned with beta. Thankfully, the pleochroic color schemes for iron-rich Cordierite are known. Alpha is associated with little color, whereas beta is associated with a violet color. As such, our view currently must be aligned with beta. And figuring this out has actually allowed us to completely orient our sample. So what we've done here is use a combination of crystallography and the optical properties of our mineral in order to figure out how it's oriented in space. But now what we want to do is take this a step further. Let's pretend I'm not really sure this is Cordierite. I have a good inkling it is, but I'm not sure. So what we can do, however, is use our optical indicatrix to make predictions for what different colors we should see as we rotate this cube of Cordierite onto different faces. And this will help us understand biaxial materials in the process. So what I'm going to do here is rotate our cube 90 degrees to a different face in the north-south direction. And as you can already see, the Cordierite is exhibiting a different color. Doing the same rotation to our optical indicatrix means we should be looking down onto the alpha-gamma plane now. Basically, we started out viewing our sample in this orientation. Then we did our 90-degree north-south rotation, which effectively is going to take beta and replace it with gamma. And so we've ended up here in this orientation. And so we've stumbled into directly looking at the pleochroic color associated with gamma. It's not quite as dark as beta, but it's still a nice deep blue color. Which is good given what our pleochroic color scheme told us earlier, in that gamma should also be a violet color. So that's another piece of evidence that this is indeed Cordierite. So now let's rotate our sample, and you should be able to tell me what we're going to see as we rotate 90 degrees. So as we rotate, we go from our color associated with gamma to our color associated with alpha. And let's reset and bring in our upper polarizer to see how things look with crossed polarizers. So as we bring in our upper polarizer, we see that no light is transmitted, meaning that we're probably pretty nicely aligned with gamma. We then begin to rotate our Cordierite and light starts to be transmitted, and then we once again transition into extinction as we line up with alpha. So we've got one more viewing direction through our sample, and it's going to be associated with the beta-gamma plane. So let's reorient our sample to that viewing direction. What I'm going to do here first is just rotate us back so that we're looking at gamma again. And then I also did a little 90-degree east-west flip there too. And so we should now be looking down onto the beta-gamma plane. And we've seen this pleochroic color before. This is the color we associated with gamma. So let's look at a couple diagrams now just to show what that orientation change was all about. We started off with this view looking down onto the gamma-alpha plane. Ultimately, we rotated our sample 90 degrees in an east-west direction. And so alpha should now be replaced with beta. So our new view, of course, is of the beta-gamma plane. And so when we rotate our sample in plane polarized light, we should transfer from gamma, which we're seeing currently, to beta, which was our darker color earlier. So as we rotate the sample, it gradually darkens as we transition from the lighter gamma to the darker violet beta. And once again, we'll now take a look at our sample under cross polarization, and then we'll take a look at some summary figures to hopefully bring everything together. I know we've been through a lot so far. So let's bring in our upper polarizer, and as you can see in this orientation, there isn't really any light being transmitted. As we would expect being aligned with beta, we then begin to rotate the Cordierite and we see light being transmitted, and then we go back to extinction when we line up with gamma. So we've now viewed our Cordierite in 3 different orientations that are important for us to understand biaxial materials. We've viewed this sample looking down onto the alpha-beta plane, the alpha-gamma plane, and the beta-gamma plane. And we used the pleochroism of Cordierite to help orient us in space. Each of our 3 properly oriented views of our Cordierite had 2 pleochroic end-member colors associated with them. And we have a total of 3 different pleochroic end-member colors for our biaxial material. We can also summarize our views that we've seen in cross-polarized light, but that's also kind of boring because most of them are just darkness whenever we're aligned with either alpha, beta, or gamma. So, with our biaxial minerals, we're always going to be hunting for these 3 views in order to figure out what's associated with alpha, beta, and gamma. But most of the time, unless we're really lucky, we're going to actually be seeing a different, more random elliptical section through the optical indicatrix. So now I just want to talk a little bit about our views that we can see if we're not looking down either alpha, beta, or gamma. So let's imagine the elliptical section that would be generated if we looked through our optical indicatrix in the following manner. So remember, the ellipse that we view is going to be generated by a plane passing through the optical indicatrix perpendicular to our direction of viewing. And in this instance, our ellipse would look something like this. It would have axes of alpha and gamma prime, with gamma prime being a refractive index somewhere in between gamma and beta, similar to how epsilon prime works with our uniaxial materials. So compared to our earlier viewing directions through the optical indicatrix, this one could be somewhat useful, but it would be hard to be able to figure out what exactly was going on. And that's really a key issue here when having sort of random views through our crystal and therefore our optical indicatrix. So oftentimes you really need something like a cleavage plane to give you an idea of crystallographic orientation in order to fully understand what's going on. So let's try another sort of random view through our optical indicatrix and see what kind of ellipse it generates. So this really off-kilter view will produce an ellipse that looks like this. In this case, we're not really aligned well with any of our refractive indices, and so we end up with an ellipse with axes of alpha prime and gamma prime. Gamma prime is once again a value between gamma and beta, and alpha prime is a value between beta and alpha. And so if we were trying to figure out what was going on with our pleochroism in this view, we'd have some issues, right? We wouldn't really be able to figure out a pleochroic end member color. They would be kind of blends. So basically what I'm trying to say is, for our biaxial materials, we really want to figure out what's going on with alpha, beta, and gamma. And so these other views aren't super helpful. Well, except for this next one. So let's imagine taking this view through our optical indicatrix now, and what kind of ellipse would we generate with this view? The awesome kind, that's what, because what we end up generating is a circle. So this view is looking down one of our two optic axes, and with this view we know we're definitely seeing beta, and it's one of the reasons this view is important, because if we can hunt down this view, we know what's going on with beta. How might we find this view? Well, it should be at extinction no matter our rotation under crossed polarizers, and in plane polarized light it should exhibit no pleochroism because we're only seeing beta. So I wish I had cut some Cordierite so that we could actually view it down the optic axis, but unfortunately I haven't done that yet, so I'll have to add that to my list of projects. But our big take-home is essentially that we have four main views that we want to hunt for when we're looking at a biaxial material. We want to hunt down the gamma-beta plane, the alpha-beta plane, and the gamma-alpha plane, and our optic axis. These views will give us the most information. Now you may also be saying to yourself, hey, you were pretty much saved by that cleavage plane, weren't you? That seems like that was really important in figuring out pretty much everything else that was going on here. Is there a way I can find these views without already having a crystallographic direction to aid me? Or maybe I just want to ensure that I'm actually looking at the view I think I'm looking at. And yes, there's an answer to these questions, and they're based on interference figures. So our next step was actually going to be looking at the interference figures seen in each of these views of our Cordierite. And these are important because they can let you know whether or not you're actually looking at these planes. But unfortunately, I haven't had much luck generating these interference figures with my current setup. As you can see, my Cordierite sample has some fractures and some inclusions going on, so I think it might not be quite optically up to the task of generating the interference figures we want. And so at some point in the future, I'll make an addendum to this video, perhaps using a different mineral, in order to illustrate the biaxial interference figures that we could possibly see. For your reference, they would be a flash figure if we were looking down at the gamma-alpha plane, a BXA figure if we were looking at the gamma-beta plane, and a BXO figure if we were looking at the alpha-beta plane. And if we managed to look down one of the optic axes of our biaxial material, we'd see a biaxial optic axis figure. Also just note that the BXA and BXO figures are dependent upon whether a mineral is uniaxial negative or uniaxial positive. Cordierite is uniaxial negative, but if it were uniaxial positive, the BXA and BXO figures would switch their respective planes. So now's the time where I want to start mentioning all the caveats we have with our Cordierite. The first is simply that when comparing our actual Cordierite to our Indicatrix, I don't actually know what the refractive indices are for the Cordierite I've shown you today. The pleochroism appears to be Ferroan, so I picked refractive indices for our diagram associated with a very Ferroan Cordierite. Which brings us into our next caveat. I don't want you to take this shape that I've shown you as the indicatrix for Cordierite. It's an exaggeration and a representation of the differences in the refractive indices. And further, since we don't actually know what the refractive indices are, perhaps even this would have been a better representation of the indices of Cordierite. So far we've talked a lot about Cordierite, which is an orthorhombic biaxial mineral. And we started out with this orthorhombic mineral because it's respectively simpler. All of our crystallographic directions and our refractive indices align. But this isn't the case when we get into monoclinic and triclinic minerals. So for monoclinic minerals, the B crystallographic axis will align with one of our refractive indices, but the A and the C crystallographic axes will not. In this case, I made gamma align with the B-axis, but that doesn't have to be the case. It can literally be any of our refractive indices. And for triclinic minerals, none of our refractive indices and crystallographic directions align. So I'm not even going to try and illustrate that. I imagine you get the idea. But the fact that our optical directions and crystallographic axes don't align actually generates another interesting phenomena for us, known as an extinction angle. So for our monoclinic and triclinic minerals, often our crystal forms make interesting angles with extinction positions, and these angles can be helpful in identifying minerals. Unfortunately, I don't really have any great examples of this, so this is another thing that's going to have to wait for the addendum I produce at some point. So I think I've done enough yammering for one video, so let's review what we've learned today. Our biaxial minerals are defined by three refractive indices, alpha, beta, and gamma. Because of the three refractive indices, they have two optic axes, and the crystallographic and optic orientations of these biaxial materials are more complex than our uniaxial ones. But if we can identify a substance as biaxial, we know it has to belong to either the orthorhombic, monoclinic, or triclinic crystal system. We talked about optical indicatrices for biaxial materials, which are triaxial ellipsoids with our axes being alpha, beta, and gamma. These ellipsoids will have two circular sections of radius beta, and our optic axes are perpendicular to these circular sections. When looking down our optical indicatrix onto the alpha-gamma plane, these two optic axes will also make an angle with one another, which is known as our 2V angle. If our two optic axes are more closely huddled around the direction through our indicatrix associated with alpha, it will be biaxial negative. If the optic axes are more closely huddled around gamma, it will be biaxial positive. Another way to think about this is whether our refractive index beta is closer to alpha or gamma. If beta is closer to alpha, then our sample will be biaxial positive. If beta is closer to gamma, then our sample will be biaxial negative. So we then took our knowledge of biaxial indicatrices and applied them to Cordierite, an orthorhombic biaxial negative material with a really nice pleochroic color scheme. And if you look at our optical indicatrix here, you'll notice the color scheme actually is shown in the axes. It was there the whole time. We talked about how the mineral Cordierite has a solid solution series within it between magnesium and iron, and we were looking at an iron-rich Cordierite based on the pleochroic colors that we saw. We then used a cleavage plane and the pleochroic colors that we saw to orient our Cordierite in space. And, once having done that, we examined the pleochroic colors associated with the alpha-beta plane, the gamma-alpha plane, and the gamma-beta plane. Doesn't it make you want to go back to the simplicity of our uniaxial minerals? Ah, epsilon and omega. We also examined our Cordierite under cross-polarized light, and showed again how light is only transmitted under cross-polarizers when not aligned with either alpha, beta, or gamma. We then talked about how different views through our Cordierite were either more or less useful, and explained how a view down the optic axis is actually pretty useful because then we know we're seeing beta. We mentioned then how we can use interference figures to aid us in ensuring proper orientation of our Cordierite, but unfortunately I don't think my Cordierite was up to snuff in order to generate them. So at some point in the future, I'll make an addendum and show off some biaxial flash figures, obtuse bisectrix figures, acute bisectrix figures, and biaxial optic axis figures. The last topic we covered was that in addition to orthorhombic materials like the Cordierite we looked at today, monoclinic and triclinic materials also fall in the biaxial camp. However, they're a bit more complicated, as all the crystallographic axes and our optical directions don't align. In monoclinic materials, the B crystallographic axis is aligned with one of our optical directions, but the C and A crystallographic axes are not. And in triclinic materials, none of our crystallographic axes align with any of our optical directions. So that's pretty much it. You've made it all the way through. So thanks for watching, and at some point I will try and develop that addendum with the interference figures for our biaxial materials. I'm also going to try and keep developing some videos, but I'm going to do these with a specific purpose. And that is that I'm interested in trying to sell some of these optically oriented mineral samples in order for people to use them as teaching aids, or just to appreciate their intrinsic coolness. So my next series of videos will deal with that, and I think I'm going to start off with corundum. As you saw in our uniaxial video, I feel pretty confident about my ability to make those. Alright, have a nice day!